students, today we'll study gravitation, and in the lecture 2 we will study the Kepler's law. Now, renowned scientist Kepler, he stated 3 laws that is related to the planetary motion. So as you know that here in this lecture, we will study that thing. So Kepler's law of planetary motion. Now, you know that there are several planets we have, but all these planets, those are revolving around the sun. So this is the main sun, and whatever the planet you have, all those planets will just rotate, that revolve around the sun. And this path which it will follow, every planet will follow, that is elliptical path. Okay. So here in astronomy, Kepler's law of planetary motion are 3 scientific laws, those describing the motion of the planets around the sun. Generally, whenever we are just going to study the motion of other planets also, including our Earth, suppose Venus, suppose Mars, or everything, or you want to analyze whatever the motion of the moons of every planet, at that time we require these laws, right? So here, first thing, that is the Kepler's first law, and it is, just a minute, I am taking the highlighter here. The first law, that is the law of orbits. First law, that is the law of orbits. So here you have law of orbits, and this one is the first law. We will describe elaborately what is the law of orbits. And in the second law, Kepler, he stated regarding the areas, that is the law of equal areas. And in the third law, he stated law of periods, that means time periods. Okay. So in every case, whenever one planet will revolve at that time, and it will follow the path of elliptical path, and it will just revolve that sun or some moon of the planet, that will revolve. At that time, you can see that it will take a particular time period, right? So suppose this is our Earth. Okay. Suppose this is our Earth, and we have moon also, and that moon will revolve here. At that time, you can see that, suppose, just a minute. So let it be Earth, let it be moon. So if it will rotate, at that time, some particular time period we have. And another thing we have, that is the radius. That is the radius. Here, you have some radius here. Okay. So that time period and radius, whatever the relationship between this radius and the time period, as you know that we have the sun here, let it be your sun, and we have some planets in this elliptical, that is our Venus, it may be Mars, it may be Earth. So every planet has different orbit, and in this orbit, every planet will just make one motion around the sun. So for every motion, it will take some time period. So whatever the relationship between the radius, and the radius is also different. From sun to Venus, whatever the radius, from sun to Mars, you have different radius. From sun to Earth, you have different radius. So that means the time period also, that is dependent on the radius of the elliptical orbit. So that we will demonstrate in the Kepler's third law. And So here whatever I have told, that Kepler's first law, this law is related to the law of orbits. Kepler's second law, that is related to the law of equal areas. Kepler's third law, that is related to the law of time periods. Okay, let's move to the next slide. Here in this picture you can see that there is a, here you can see that there is a planet which is revolving here, right? So now you can see this sun is at the foci of this elliptical path. So this one is our, just a minute, I am writing this one. This one is our elliptical path. Okay, and in this elliptical path we have foci, that this is an S dash. Now in the Kepler's law, first law, all the planets revolve around the sun in elliptical orbits having the sun at one of the foci. So in this elliptical orbit you have, this is one foci. So here S and S dash, this is actually S dash. So these are foci. Okay, so here you can see that, here you can see that all the planets revolve around the sun in elliptical orbits having the sun at one of the foci. So here we are just taking one orbit, but if you have the sun here, that means you have several orbit around this, right? And how so many planets are there. For Venus there is separate orbit, for Mars there is separate orbit, for Earth there is separate orbit, also for Pluto there is separate orbit, also for our other planets. Every planet has a dedicated orbit, until unless it may be they will collide. So that should not happen at that time. So every orbit here, for every orbit, whatever the foci, there are two foci, but here whatever the foci you have, the sun is at one of the foci, right? And the point at which the planet is close to the sun, that is known as perihelion. Here you can see that the P point, here this is the sun, it is situated at foci, that S. Now this P point, that is very nearest to the sun, right? So the point at which the planet is very close to the sun, that is called perihelion. Okay, that is called perihelion. At the point at which the planet is further from the sun, that is called, this point A, that is called aphelion. Okay, so you should remember these two terms. One point that is very close to the sun, another point that is very far away from the sun. So which point is very close to the sun, that is called perihelion, and which point is that is far away from the sun, that is called aphelion. Okay, clear about perihelion and aphelion? Now here there is a characteristics of an ellipse. What is the characteristics of the ellipse? Because we are talking about this ellipse here, because we are talking about the elliptical orbit. So that means the characteristics of ellipse will be applicable here. So the characteristics of an ellipse is that the sum of the distances of any planet from two foci is constant. Okay, so the sum of the distances from any planet from two foci is constant. So I am just trying to draw one here. Suppose this is the sun and one elliptical orbit is here. There is some planet here. Okay, there is some planet here, and in this orbit, Sorry, just a minute. Just a minute. This line is not so much straight. I just want to draw one straight line here. Okay. So suppose this is one foci. This is another focus. Now, whatever the distance, and the sun is situated here. The sun is not there. Just a minute. Okay. Now it's correct. So here, whatever the distance you have from this foci to the planet. So suppose this is the distance from foci to the planet, from this point, A point, and let it be A dash point. So the sum of these two distances are constant. Okay, this value is constant. And the elliptical orbit of the planet is responsible for all the occurrence of all seasons, right? So in Kepler's first law, what we have studied, all the planets revolve around the sun in elliptical orbit, and having the sun, where the sun is situated, another point you should mention, the sun is at one of the foci, right? So in the Kepler's first law, 2 points are very important. First point, that is the all planets revolve around the sun in which type of orbit? Elliptical orbit. And the second point you should remember, or you should include, that is the having the sun at one of the foci, right? So one point is very important, that is elliptical orbit. Another point that is very important, that is sun at one foci, right? And from this we have studied two terms, that is the perihelion and aphelion, that the point which is very near to the sun, that is very close to the sun or near to the sun, that is called this point P, that is called perihelion, and the further point from the foci, that is called, from that foci, that is called aphelion. Okay, from the foci, that means not from this foci, that from S. Okay, so that is called the aphelion. And the characteristics of the ellipse, that is what? The characteristics of the ellipse is that the sum of the distances of any planet from two foci is constant. And the elliptical orbit of the planet is responsible for all the seasons, whatever we can feel here. Okay. Now Kepler's second law, and it is regarding the areas. Now here in this figure you can see that one planet is revolving around the sun, and here it will just make one area, and this is also another area it is making. Both the areas will be same. This thing has been stated in the Kepler's second law. What is the statement? The radius vector drawn from the sun to the planet sweeps out equal areas in equal interval of time. Suppose you have 1 day to travel. So if you have 1 day to travel, how much area you have? How much area you have here? If you have 1 day to travel in this side, the same area will be covered. Same area will be covered. Suppose this is the sun, and in this figure, this one is your elliptical orbit, and there is a planet, and this planet is moving from this point to, just a minute. Okay, this planet is moving from this point to this point, right? So from this sun, whatever the area has been, this is the area. Now, whatever the area you have, this area equal to the area whatever you have here, right? And both of them that are taking the 1 day. So, or 1 day or 2 days. But that means the radius vector drawn from the sun to the planet sweeps out equal areas in equal interval of time, right? Now, in the elliptical orbit, what happens? Here, the circular orbit is not this in this case. So we have the elliptical orbit. Now it has more kinetic energy near the perihelion and less kinetic energy near the aphelion. Okay, so here, and again I am just repeating what is perihelion and aphelion. Perihelion means the nearest point, that is nearest point from this sun, that is the perihelion, and the very distant point or further point, that is called the aphelion. So here the kinetic energy near the perihelion, that is more, and less amount of kinetic energy you have near the aphelion. So here that means what? Kinetic energy that is kinetic energy that is higher or lower. That means kinetic energy that is your how much? We know that half mv square. Now mass will be the same. Mass will be the same for both these places. Mass will not change here. But v, that is the speed, or that is the velocity. That speed. Here you can see that whenever you have you are at the perihelion, at that time the velocity is high, and whenever you have you are at the aphelion, at that time your velocity will be small, velocity will be low. So at the position of perihelion, let it be this point, we are taking the velocity is v max, and at this point, let me change the pointer color until unless I cannot explain anything. So suppose this one is your, this point, this is your aphelion. So farthest point, or p dash or p, whatever, these are the farthest point. So at this point you have the velocity vb. Okay, and whatever the radius, whatever the distance, or the whatever the distance, here I cannot say the radius, whatever the distance from the planet and in between the planet and the sun, suppose this distance, this one is your r min. Okay, this distance is the r min. It is visible, r min, and this distance, that is your r, let it be r max. Okay, so that means this is the r max and this one is your r min. So r min plus r max, that equals to twice a into length of major axis of an ellipse. Okay, twice a into length of major axis of an ellipse. Okay, so here this is the Kepler's second law. The radius vector drawn from the sun to a planet sweeps out equal areas. You should mention this term, equal areas in equal interval of time. We are not saying for different interval of time. Remember this thing. If you are thinking about 1 day of traveling, then this will be the area. The color is not so good. Let's change the color. So here you can see that this will be the area, and whenever you have the same 1 day, this will be the area. Both the area will be same. But remember one thing always, for equal intervals of time. Again, I am repeating the term, for equal intervals of time. Okay, so this you should remember. Now Kepler's third law. Here the law of time periods. Now according to the Kepler's third law, here the square of the time period of revolution of a planet around the sun in the elliptical orbit is directly proportional to the cube of semi-major axis. Cube of semi-major axis. Semi-major axis means the distance between this sun and this planet. So this one is the planet, whatever you have, and this one is the sun. So this is the major axis. So here semi-major axis. Now, so according to Kepler's law, what he has said, the sun, whatever the square or time period square, this time period square, where t is the time period of what? The planet is taking how much time to revolve, okay? And r, this is the radius of the, or distance. Just a minute, I have to write the distance. I have to write the distance. Distance. This is the distance. Now, this distance is what? This distance is the distance between your sun and this planet, or the distance of the semi-major axis, right? So, the time period t square, that is proportional to AQ, okay? The square of the time period of revolution of a planet around the sun in an elliptical orbit is directly proportional to the cube of its major axis, semi-major axis. And shorter the orbit of the planet around the sun, shorter the time taken to complete one revolution. Can you tell me any one planet which has shorter orbit? Here we can think about the Venus also. It has shorter orbit. Pluto, that is very far away. So it has a very, or here at that time, the semi-major axis, that distance is very high amount. Okay. So here, this is the Kepler's third law, or law of periods. Sometimes we are calling this that law of time period. Okay. Now, if you have multiple planets that is revolving around the sun, so here it is sun, let it be planet 1, let it be planet 2, and it looks like Saturn, right? So here, whatever the time period T1, let it be time period T1, this is the time period of planet 1, and R1, that is the distance of semi-major axis, and T2, time period of planet 2, R2, distance that is regarding the planet 2, and this distance is regarding the planet 1. So T1 by T2 square, that equals to R1 by R2 whole cube. R1 by R2 whole cube. Okay. So here that T1 by T2 whole square, that equals to R1 by R2 whole cube, or I can write T1 square, that equals to R1 cube, and T2 square, that equals to R2 cube. Okay. Now, several questions may come. First question may come regarding the Kepler's first law. What does Kepler's first law explain? So here, all planets, what do you know regarding the first law? All planets revolve around the sun in elliptical orbit. First point you should mention here. And the second point, what I have told you, that with the sun as one of the forces. And what does Kepler's second explain? In the Kepler's second law, I have told you, you can explain regarding the area, of the revolution. Okay. And here, what is Kepler's third law? In the third law, we may think about the time period. So here T squared, that is proportional to your R cube. Okay. So Kepler's third law, that called the law of periods, states that square of the orbital period is proportional to the cube of its mean distance R. Okay. Why are the orbits of planets not circular? Here it requires the planets to travel with a certain velocity, and which is extremely unlikely if it will be circular. So if there is any change in the velocity of the planet, the orbit will be elliptical. Okay, so here the elliptical is preferable. Now let us do some numericals regarding this. So Titan, oh okay, Titan. Let me change first the ink. Okay, solution. Titan, the largest moon of Saturn, has a mean orbital radius of 1.22 into 10 to the power 9 meter. So always I have told you, first write down the given data. So given, what has been given here, the Titan is the largest moon of Saturn, has a mean orbital radius 1.22 into 10 to the power 9 meter. So radius of here Titan, radius of Titan, this is obviously orbital radius, that equals to 1.22 into 10 to the power 9 meter. Fine. Now orbital period of Titan is 15.95 days. So orbital period of Titan, that equals to, we are thinking this is our T, and this is our RT. So that equals to 15.95 days. And Hyperion, another moon of Saturn, orbits at a mean radius of 1.42 into 10 to the power 9 meter. Okay, fine. So orbital radius of Hyperion, let it be R H, that equals to 1.48 into 10 to the power 9 meter. And here use Kepler's third law of planetary motion to predict the orbital period of Hyperion in days. Okay, so orbital, let orbital period of Hyperion, that equals to TH. So we can write Kepler's law, third law, using Kepler's third law, using Kepler's third law or law of period, we can write TH divided by TT square, that equals to RH by RT cube. Okay, now you put all the values, so you will get here RH cube by RT cube, where RH is the 1.48 into 10 to the power 9 whole cube divided by RT whole cube, where RT is the 1.22 into 10 to the power 9 whole cube. So from this we will get TH, that equals to square root of 1.48 into 10 to the power 9 whole square into 15.95. This divided by 1.22 into 10 to the power 9 whole square. So here I am writing. So TH, that equals to 21.3 days. 21.3 days. Okay. So here answer, that is the orbital period of Hyperion is 21.3 days. Okay, fine. This much. Next, here the mass of the earth is, let's solution this one. Mass of the earth is 5.97 into 10 to the power 24. So let mass of earth, that is denoted by ME, that equals to 5.97 into 10 to the power 24 kg, and mass of moon, that is 7.35 into 10 to the power 22 kg. So mass of moon, we are taking mm, 7.35 into 10 to the power 22 kg. Mean distance of the moon from center of earth is 3.84 into 10 to the power 5 kilometer. So mean distance R, that equals to 3.84 into 10 to the power 5 kilometer. We convert it into meter. So 3.84 into 10 to the power 5 into 10 to the power 3, that means 10 to the power 8 meter. And G, if they will not give the G at that time, you have to remember the gravitational constant. This is 6.673 into 10 to the power minus 11 Newton meter square per kg square. And here we have to calculate the gravitational force. So gravitational force F, that equals to G ME mm divided by R square. So if we put all the values, F equals to 6.673 into 10 to the power minus 11 into 5.95 into 10 to the power 24 into 7.35 into 10 to the power 22 divided by 3.84 into 10 to the power 8 whole square. That means it is 1.99 into 10 to the power 20 Newton. This is the answer. So, just a minute. Okay. So here, answer, the magnitude of the gravitational force exerted by Earth on the moon is 1.99 into 10 to the power 22 Newton. Okay, this much. Now, what is acceleration due to gravity? Now, acceleration due to gravity, generally we are, just a minute, I am just changing the color of this. Okay. Okay. So, the acceleration due to gravity we are denoting by G, and it is 9.8 meter per second square, right? And SI unit is the meter per second square. So the symbol is G, and acceleration due to gravity, that is the acceleration gained by an object due to gravitational force. That means what? Whenever some object, some body that will fall towards the earth, at that time, whatever the gravitational force that the gravitational force will be acting, at that time the body or the object, it will gain some acceleration. That is called the gravitational acceleration, right? So here the SI unit is meter per second square, and formula, that is G equals to Gm by R square, and value is the 9.8 meter per second square. Now calculation of G, this is important but less important. Here the force, always we know that what? Mass into acceleration. Force, we know that that is mass into acceleration. Now what is the acceleration here? The acceleration, that is our G. Okay, so we can write down that F equals to m into G. Now again, if there are two objects, one have the capital M, that is the mass of the earth. Here capital M, that is the mass of earth, and small m, that is the mass of object or body. So we know that the force that will be our, we know that from these two, we know that the force, that is nothing but G m into capital M divided by R square, where R is the distance between these two objects. One object is earth, another object is the body, whatever you are keeping, right? So these two forces are equal. That means if we cancel this m, at that time we will get G is nothing but that your G into capital G, gravitational constant, into the mass of the earth divided by the distance between the two objects, that means the distance from the earth, R square. So this is the calculation of G. Now here for acceleration, if we calculate at that time, G is how much? You know that 6.673 into 10 to the power minus 11, and mass of earth, that is 6.0 into 10 to the power 24 kg, and R, that is 6.4 into 10 to the power 6, so whole square. After evaluating this thing, you will get 9.8 meter per second square. That's why it is 9.8 meter per second square. From so many chapters, we have used that G equals to 9.8 meter per second square. If you remember the chapter of motion also, at that time we have used some object that is falling towards the earth, or some object I am just going upward, that means vertically upward. At that time we have used some G value. So the G value is 9.8 meter per second square. Why? That has been explained here. Okay, that means the difference between gravitational constant, that is denoted by capital G, and the gravitational acceleration is that the gravitational constant value is 6.673 into 10 to the power minus 11 Newton meter square per kg square, whereas this acceleration is 9.8 meter per second square. And this is a scalar quantity, but this is a vector quantity, because the gravitational acceleration, that acceleration, whenever some object is falling down to the earth, at that time it will act here. So this is the gravitational acceleration. If I am just throwing one ball upward, at that time the direction will be different. So it is a vector quantity. And gravitational constant, that gravitational constant, it remains constant always and everywhere. But the value of the G, that is not equal for everywhere. Okay, it can vary, because here you know that the gravitational constant, that is the G into m divided by r square. So if you change this r, the mass of the earth, it cannot be changed. Fine, G will not change, but r can be changed, and G is inversely proportional to 1 by r square. So this radius may change. That means the gravitational acceleration may change. And in case of unit, Newton meter square per kg square. And here the unit of the gravitational acceleration, meter per second square. Okay. Thank you.